Okay, so it's a pleasure to introduce Dr. Carlos Mera. Dr. Mera got his bachelor in physics at Universidade do Atlântico in Colombia. Then he came to USP São Paulo and got his master's and PhD in physics there. Then he did a series of postdocs and visiting researcher positions outside the country at the Max Planck Institute in Berlin, the University of Washington. He then came back to the LN Nano in Campinas, the Federal University of ABC, and then another postdoc in Colorado Boulder, and now he's back at USP São Paulo. And today he's going to talk to us about the different shapes of spin textures as a journey through Brillouin Zone, spin electronics applications. So, Dr. Mera, thank you very much for accepting our invitation, and you can start as you please.
Thanks, Jordan. It's always a very big pleasure to be in Overlandia, even virtually. It's the home, very nice friends and a very good scientists. So it's always nice to visit you. And thanks a lot for the nice invitation. Well, yeah, I'm currently working on at the ABC Federal University, finishing the last postdoc, I wish. So, and yes, as you mentioned, thanks for the introduction. I'm going to discuss about the different shapes of the spin texture in the same component, but when we move from one K point to another. So I'm going to explain this and try to discuss that in the context of materials. And to make clear what is the problem we are trying to solve here, I'm going to start by making a parallel between a very simple problem about band structures and the problem of spin polarization and spin texture. And then I'm going to define what is this spin texture, okay? So one nice thing is that our paper was published 2 days ago. So I was ready for this conference, this meeting. And well, in this paper, we start with this discussion of the definition of a spin polarization and what is the relation with symmetry. I'm going to follow a similar outline here, and then I'm going to explain some examples of the connection between spin polarization and symmetries. And finally, I'm going to use this to filter some compounds. So, well, essentially, what is the first problem that came to our mind when we think on spin polarization? Well, it turns out that there is a historical reason for this this kind of problems that is related with the fact that in the recent years we have invested some time on understanding topological insulators and some related problems. And the main idea is essentially that when we have something like a bulk material, and this material is a topological insulator, then we expect to have some surface states. And the basic idea is that the surface state has some spin polarization that is helical. This means essentially that the spin is always perpendicular to the momentum. Well, it turns out that this kind of spin texture is then related with the topological behavior, with the strong spin-orbit coupling. However, when we look to other kind of systems like Rashba compounds, this means compounds that have an electric dipole, or even electric dipole plus an intrinsic magnetic field like Zeeman compounds, then we observe that the spin polarization is actually very similar to what we expect on topological insulators. So the big question that appears here is the following. Is the spin texture, this is kind of a spin polarization, a consequence of a functionality like the topological protection, or is something related with the electric field? So what is the mechanism, the physical mechanism behind this kind of behavior? So this is the first question, and I'm going to explain this and try to relate this kind of spin polarization and behaviors with the symmetry. And so let me try to explain this why this problem is important, why we would like to understand it. And I'm going to start then from the very beginning. And I know that most of you are almost expert on this field. However, I would like to mention a couple of very basic things for students and people that is not very familiar with this field. And first, to again try to explain why to understand the polarization terms, the spin polarization in terms of symmetry is very important. And second, why we usually relate it with a specific phenomena like topological insulators or ferroelectricity or even Rashba. Okay, so essentially the current view of our technology based on semiconductors is essentially related with the fact that we think that when we put things together, we are able then to understand what is happening only by understanding the basic building blocks of the system. For instance, when we put electrons together in an atom, for instance, then we are able to understand what is happening. And this starts with understanding of the electron and then the interaction between them and the model of the atom, orbitals and so on. But the nice things appear when we put atoms together in a periodical lattice, okay? And then we are able to understand again when we put atoms together what is happening with the interactions and how this gives us a very basic understanding of something like the Venn structure, okay? So what is the point with the Venn structure? Well, it's maybe, in my opinion, is a very beautiful consequence of all the way in which we construct our interpretation of materials, because we're able not only to understand very basic phenomena, but also to classify all components that we know in these classes of metal, semiconductors, and insulators, for instance, and sometimes even topological insulators, only using this very basic interpretation or abstraction of the idea of material. So the point is the following. The Venn structure is usually this is essentially this very basic idea that not only classifies the materials I already mentioned, but also is used to construct then our technology like transistor and these things. For instance, as we know, we can do make us transistor like MOSFET here in this case. And the point is that when we try to increase efficiency and also increase the number of transistors we have in a chip, we see that the tendency is try to following the Moore law. Okay. However, we are very near because of quantum tunneling and other intrinsic phenomena of the wave function of electrons in the limit of this miniaturization. Okay, so this is a very big situation problem for the efficiency to follow and also to follow the Moore's law. So as alternative to the technology basis on the electrons appears the spintronics, not now the electronics, but the spintronics, and the idea is to use the spin of the electron as the basic element of the technology. So now everything is about the spin of the electron, and the idea is essentially to have something like a transistor. So we can, for instance, have two electrodes here in a central region, and the electrons go from one electrode to the other. And the idea is that if we have a magnetization for these electrodes, we then are able to control the probability of the specific spin of the electron here in the central region to have quantum states to be detected in the drain, in this electrode in the right side of the plot. So this essentially requires the control mechanism, a control mechanism in the central region. So essentially, we would like to have a spin current here and use, for instance, a external electric field to change the direction of the spin. So we are able to say, okay, now, for instance, when the spin is the same of the magnetization in the right side, so we will have the possibility of have a non-zero probability to have a transition here between the central region and the right side of the device. But when the spin is contrary, I mean, is opposite in, so we have that there is no a probability to have this transition. So essentially, if we control the direction of the spin, we are able to construct 1 and 0. 1, for instance, where we have a non-zero spin current, and 0 when there is no any probability to have this kind of quantum transition, this kind of transition. So there is no any possibility to have states in the other side, and then we can say that this is 0. And using this 1 and 0, we are able to construct the basic idea of transistors in using spintronics. I mean, this is the main idea of spintronics. So now that I try to put this concept and try to explain that the spintronics is important, so we would like to really understand what is happening with the spin in the compound. I would like to also convince you how to do that. I mean, what is the main idea of this? So now we already know that we would like to have a spin because it's easy to control. We have a larger lifetime in the device, and we don't have this the same problems that we have about quantum tunneling on the electrical current and so on. But now that maybe you are convinced that spins are good in compounds, so let me try to explain why we already don't understand them, why we don't really know what is happening, what is the relation with symmetry in general, okay? So the idea is now that the same picture that we construct in the last 100 years about the electrons in compounds and atoms and so on, now we need to do the same thing, but using the spin, okay? So we need to add the spin to our picture of atoms. We need to add the spin in our picture of solids, and we also need to add the spin in our interpretation of Banach structure. So essentially now all the states in the Banach structure have spins, okay? A spin up, down, or different directions. If you consider, for instance, a spin-orbit coupling, I'm going to explain that later. But then the real, let's say, street we would like to use to work in this new or novel possibility to construct devices is essentially in the context of spintronics, and is related with the generation of spin currents, detecting spin currents, and controlling the spin currents. But to do that, as I already mentioned, we need to understand how to first put the spin in the Banach structure and how it appears. So, and maybe you are thinking that this is very simple and obvious, but let me try to convince you that it's not so easy, okay? Well, to do that, I'm going to use a parallel description between the Banach structure and the spin, as I mentioned before. And let me try to show you the following things. Banach structure, well, appears when we have interacting orbitals in a lattice, and as we already discussed here, allows us to classify compounds in terms of the topology, allows us to understand the effective mass in compounds and so on. But the nice thing to see is that the Banach structure for many years was essentially an output. You know, essentially I'm trying to say that if you have the element, you have the Vicos positions, the lattice, the interaction between the atoms, and the potentials you have in your compound, you are able then to have the Banach structure by using for instance, time-binding model, a K.P model, or for instance, using a density functional theory, and just put the whole information of the compound in a code, for instance, and then get the Banach structure after a few seconds, few minutes. Essentially, now we have a lot of Banach structures for more than 200,000 compounds and very big databases with the whole information of the Banach structures. And this is the concept of the Banach structure. I mean, the whole interpretation about the electron, the complete interpretation about the electron in a compound, okay, without, of course, without a strong correlation, but the whole mean field theory of the electron in a compound, describe it as an output of a calculation. This means the solution of the Schrodinger equation. However, it came in the recent years, we saw that there is a parallel, let's say, interpretation that is essentially the same. We got essentially the same result. Okay. However, now the Bennett structure is not just an output, but is a symmetry element. Okay. And maybe this can sound, this seems a bit, this statement seems a bit strong. I mean, symmetry element. But let me try to explain. Again, if you have, for instance, the elements, vehicle position, lattice, and the whole information defining the component, then you are able to understand how the orbitals in the reciprocal space induce degeneracencies in the band structures. So you are essentially able to understand what is the symmetry representation of each band that you are able to have in your component for the given lattice, vehicle position, elements, and so on. So the main idea is that you are able to understand this degeneracencies here, how many you have in your system, and for each K point in the Brillouin zone. And now you are also able to understand how to connect them. I mean, how you can go from one K point to another, and what is the symmetry rule connecting one degenerated state in one K point to another. Okay, so essentially you're only using symmetry information, okay, and of course, what orbitals you have and so on. You are, without solving the Schrodinger equation, you are able to understand what is the basic plot of the Bennett structure. The details of the energy, I mean, how large, big, small, and so on, is the specific values, splitting, and these things, is of course requires to make a calculation. I mean, the solving Schrodinger equation. However, the whole information here of the component is inside this concept of symmetry here, and this was developed by the Bernard B. group 4 years ago. It was published in Nature. It's a very beautiful paper that I'm pretty sure you all discussed before. So, well, now, what is the relation of this story with the spin texture? Well, if we put now the spin in the electrons, in the electrons, in the atoms, in the components, and now we have it in the Bennett structure, it turns out that the spin, the story of the spin, is also related with an output of a calculation. What this means? Essentially, that the spin polarization is the expected value of the spin operator. This is the spin operator computed for a specific band index and K point. So if you have the wave function, I mean, if you solve the Schrodinger equation, you are able to compute this expected value, the expectation value of the spin operator. So you are able then to put these arrows that are essentially the direction of this expectation value, I mean, along the x-axis and y-axis and z-axis and so on, okay? So you can just take for each band and K point these three values and put it in a plot, and then you will see the spin texture. And this is the idea. And it's very nice how this output give us a basic idea of what is happening with the spin polarization for specific components. For instance, we know now that when we have an electric dipole, we expect to have something like this pattern, this spin polarization pattern here. And look for 1 second here that the spin, for instance, blue and red, which means the clockwise and anti-clockwise helical spin in a bands that have a splitting here. These have two bands, red and purple. Well, these two spins, red and blue, are always perpendicular to the momentum. If you put here a vector, you will see that the spin is always perpendicular to the momentum, the k vector. So this usually occurs when we have an electric dipole, and we believe that for more than 60 years. I mean, once we have electric dipole, then we have this kind of spin polarization pattern. The guy that discovered this his name is Emmanuel Rashba. So we call this spin polarization pattern as Rashba spin texture, for instance, or Rashba spin polarization. We also know that even when we don't have an electric dipole in the component, I mean, we don't have a polar component, but the component is still not centrosymmetric, then we got a spin polarization like this. And this is known as Dresselhaus spin texture because the guy that proposed the Hamiltonian describing these bands here is Dresselhaus, okay? It's not Mildred Dresselhaus, but her husband, okay? And you can see here, for instance, that the wave vector now is again perpendicular to some regions, but parallel to other spins here for both blue and red colors here. And finally, just for completeness, you can see the normal Zeeman spin polarization, that is essentially the spin polarization that appears when we have an external magnetic field that is perpendicular to our sample. Well, this is the story. All of this is an output, and this is very nice. Even using this information, we now, I mean, in recent years, we make calculations for a lot of compounds, and we have a very big databases for materials having different spin texture at different K points, Rashba, Dresselhaus, and these things. And all of this story seems complete, okay? The spin texture as an output. But what about the spin texture as a symmetry element? The idea is the following. What is the symmetry behind the spin polarization patterns that impose this behavior, okay, and is always, I mean, that allows us even to a priori determine the spin polarization without making any calculation, as already is known for the Bennett structure. Well, I'm going to show this. Well, then the main idea is the following: to have the crystal symmetry, Vicos position, reciprocal symmetry point group, and using only this information, we are able not only to have the bar representation as we discussed before for the main structure, but now also to have the spin texture. So, and then this is what we would like to have in our presentation today. Very large introduction, but I think that this is important because it first put why spin polarization is important, and second, it really clarifies why we would like to do and why we would like to give the biggest step between interpretation of the spin polarization as an output and now spin polarization as a symmetry element. Well, now that I convinced you about this, I would like to mention that there are many guys working on this. For instance, we have here Edson is an expert. We also have Hiroki Tomei that have worked on that. Also, of course, Gerson have very nice works on this. But there are many guys working on that on these kind of problems. And you can see, for instance, this is from the CAPES repository, that the number of papers published containing the word spin polarization in the title of abstract has increased in the recent years, and of course we have a smaller value here of 2020 compared to 2019 because of pandemic related things, but there is a tendency to increase the number of papers, and many nice scientists are working on this and trying to really find possible routes to implement Spintronics. So, okay, so now I'm going to discuss some previous works on this subject that first trying to construct the databases to then try to then extract the information then from these databases for the understanding of the relation between symmetry and the spin polarization. So there are there are some papers we published in this previous year. For instance, as you can see here, we have this Zeeman type spin splitting. I'm going to discuss very brief what is the meaning of this. We also have this nice paper on the Rashba scale. This means what determines a large spin splitting, and second, the possibility to control the spin polarization using an external electric field. This means essentially when we have ferroelectricity and Rashba effect in the same compound. So I'm presenting these titles here because I would like to discuss at least one of them to convince you that that there is a relation between symmetry and the spin polarization. Let me try to explain very, very quick what is happening here. So in figure A, we have the band structure of a compound. This is just a schematic illustration. Okay, this is the band structure of a compound that is centrosymmetric. Okay, that is not magnetic. There is not any magnetic field. Okay, however, we move from one K point, when we move from one K point to another, we will see that K points preserving the time reversal symmetry. For instance, the gamma point here, as you can see, we have in the figure A, degenerated bands. So spin up and down should be together always when the time reversal symmetry is preserved in the K point. But when we move to another K point in which the time reversal symmetry is not preserved, so what we have is a spin splitting. So this spin splitting looks like a Zeeman spin splitting. This means essentially that we have the spin texture, the spin polarization expected when we have a magnetic field, okay? But in a compound without any magnetic field, without any intrinsic magnetic moment. So this is the idea. So this is giving us the following idea. The global symmetry, I mean, the symmetry of the compound is not really related with the spin texture we can see in the band structure, okay? So even if I have magnetic field, even if I have electric dipole or electric fields, I'm not able, using this information, to predict the spin polarization. And I hope I convince you about that, because of course we have, for instance, this guy, tin telluride, is in the figure C, is a compound that is not magnetic, okay? And we have a very huge spin splitting around the W points. As you can see here, I put a W6 and 8. And the main idea is that this W point hasn't time reversal symmetry, but the compound preserves the time reversal symmetry. So we have a spin splitting that looks like Zeeman in a compound that has no magnetic field. So if I convince you about the contradiction of interpreting the spin polarization using the global symmetry of the compound, I'm going to go to the next subject, okay? All right. And explain the following thing. Well, here we have a ferroelectric compound. This is a schematic picture of a one-dimensional ferroelectric material. So essentially, you can see, for instance, in the figure here in the middle, that this chain of atoms, this one-dimensional chain of atoms, is centrosymmetric. We have essentially that the distance between the two schematic atoms is the same in the complete change of atoms, but when we move to left or right, we will have displacement represented here, for instance, in blue, for instance, a displacement here in the positive direction, and a displacement here in the negative direction for the right side. And it turns out that this can create an electric dipole. For instance, if we consider S and p orbitals, just to give you an example. So this can create an electric dipole that is positive or negative, okay? And it turns out that when we have an electric dipole, then we have spin splitting, and when we have spin splitting, we can have spin polarization, for instance. It's not always like this, but we actually can have. And in this specific example, I put here, for instance, what we call Rashba spin polarization, just to give you an example. And it turns out that when the polarization is up, then we have this kind of spin polarization, okay? And when the polarization is down, we have the opposite spin polarization. Here, again, the global symmetry, okay, of the two chains of atoms, actually, just let me know if you confirm it, you can see that. The inner circle here have a clockwise spin polarization, but for polarization up, the inner Fermi surface have anti-clockwise spin polarization. So the nice thing here that I would like to emphasize is that in both cases, left and right, the global symmetry is the same. I mean, even if we move one atom to up or down, the chain is essentially the same. I mean, there is a unit cell formed by two atoms, and you can put like this or like this, but it's essentially the same system. So essentially, we have the same symmetry, the same global symmetry, but we see a different consequence in the spin polarization. This means the direction of the spin polarization is different even with the same global symmetry. So again, together with the previous example of Zeeman spin splitting in non-magnetic compounds, we have here an example in which the global symmetry is not able to determine, to a priori determine what is the spin polarization we can expect. I mean, at least the direction of the spin polarization. So if I convince you about this, you can find more information in this paper, this PRB paper. If I convince you about this, so and we already know that the global symmetry of the compound is not directly related with the spin polarization. So the question is, what determines then the spin polarization in a given compound? And the answer is the following. This spin polarization will be related with the symmetry of the high symmetric A point, which in turns can depend on the global symmetry, of course, but it's not the same thing. So it turns out then that for a single compound, for a given compound, we can move from one K point to another, and then if we find different symmetries, we will find different personalities of the spin polarization. And I like to put this in the with this film here, because essentially we only see one personality of the compound. I mean, usually when we do spin RPS or when we look to time binding models or K.P models, we usually look for one specific high symmetric A point. And if we don't look to the whole Brillouin zone, then we are losing information of the different personalities, the different spin polarization personalities of the compound, and we will see only the one that we have in the specific K point we are looking at. But essentially, there is a whole different world of patterns in the same compound. We just need to take care of which symmetry we are looking at. Okay, so then one example I really like to show is this. This is the gallium arsenide. It's a very well-known compound. Actually, it's already in our technology, and it's famous for many different things. But one of the things is that this compound was the one that Dresselhaus used to propose his model. So essentially, at the gamma point, that is when the point that Dresselhaus used to make the effective model, at the gamma point we have a spin texture that is perpendicular and also at the same time parallel to the wave vector. So and essentially what we have is that this remember as the Dresselhaus spin texture. But when we go to other points, for instance, this green plane here that corresponds with the L point in the gallium arsenide, what we see is that the spin texture, now in figure C, you can see here, what we see is that the spin texture, it looks like Rajba, okay? Looks like a spin texture that is always perpendicular to the wave vector. However, Rajba showed us that we need an electric dipole to have this kind of a spin texture. So essentially, we have a kind of contradiction here. Is a Rajba spin texture in a compound without any electric dipole, without any topological, non-trivial topological phase, without any big spin-orbit coupling. I mean, the spin-orbit coupling that we see, for instance, in topological insulator that is responsible in some way for the spin momentum locking effect and these things. So we don't have any of these things here. It's just gallium arsenide, but instead of look to the gamma point, we are now looking to the L point, and we see Rajba spin texture, but we don't have any ingredient that we need in a compound to have Rajba spin texture. So it's a contradiction, and this is a nice representation of the different personalities that a compound can have when we go from one K point to another. And now let's try to understand this. Let's try to understand what is happening here, okay? So, well, I'm going to use very basic rules for the spin, and I need you to please remember that the spin is a pseudo-vector, it's not really a vector. So we can define some rules for the spin direction and then use them for components. So, well, essentially, let's suppose that we have a plane, a symmetry plane, and it turns out that if we have a spin, the symmetry plane are represented here by these blue planes here, and the spin represented by this arrow here, okay? And essentially, when we have a spin here in these planes, the spin should be perpendicular to the plane to preserve that symmetry. This means that if the spin is parallel to the plane, we are going to break that symmetry. Or in other words, if we have a symmetry plane in the compound, this means that the spin should be or must be perpendicular to that plane. Otherwise, essentially, this symmetry doesn't exist. Okay. And a similar thing occurs with a symmetry axis. When we have a rotation symmetry, essentially, the spin is comfortable when it's parallel to the rotation axis. If the spin is perpendicular to the rotational axis, then this is not a symmetry of the compound, or essentially we cannot have the spin in that direction. Now we can use these two very simple rules. Of course, we have a mathematical way to describe that, but I'm not going to use this terminology here to don't bother you. Just make something more clear, okay? And let's use these two rules, just mirror planes and rotation axis, to construct a whole theory of what we can expect for specific point groups. Well, to do that, I divided the non-centrosymmetric point groups in 4 categories. These categories are defined by the chirality and the polarity. As you can see here, for instance, in blue, we have the chirality. A point group can be chiral or non-chiral, and can be polar and non-polar. So we have 4 categories described, for instance, by polar chiral, polar non-chiral, non-polar chiral, and polar non-polar non-chiral, okay? And we have very specific point groups here, for instance, C1, C2, C3, C4, C6, in the case of polar chiral symmetries. Okay, so now we can see which kind of rule these symmetries impose to the spin texture. To do that, you need to remember 2 things. First, the first one is that chiral means that you only have rotation symmetries, and non-chiral means that you have both rotation and mirror planes. Polar means that you have only one rotation axis, I mean one polar axis, and non-polar means that you have more than one rotation axis, symmetry axis, okay? So let's look now, for instance, to the first case. So now we have only one rotation axis that is perpendicular to this plane here. So there is no any rule that we can impose to the spin in this case, because we have only one rotation axis. The only rule is that the spin that is in one plane should be connected by a rotation, this rotation in green here. When we use this rotation, for instance, C4 means that the spin should be connected or should be equivalent to the spin when you give the rotation of C4. Well, now when we look at the case when we have one polar axis, this means a polar point group, as you see here in the top part of the figure. But you also have planes. This means that the polar group is non-chiral. Then you have now some symmetry rules for the spin. That is the following. The spin, as we discussed before, should be perpendicular, always perpendicular to the plane axis. The plane here, sorry, the mirror plane. And this plane is represented here by these dashing lines, the green dashing lines, and representing here the case of a C4B group. Okay, we have 4, sorry, C2Vs. Yes, we have 2 planes here, right? Okay, so and then the spin should be perpendicular to the mirror plane. So, and also connected by the rotation, the axis we have here in green. Now we can see the next situation, that is when we have only rotations in the point group, but more than one rotation symmetry. So you can see that we have this main polar axis, okay, and we have in the plane many other rotation symmetries. So essentially, as we discussed before, the spin should be parallel to the rotation axis. So this means that the spin should be always parallel to the wave vector. This is, of course, contrary to what we saw before, because in this case, the B figure, the spin should be always perpendicular to the wave vector. Then finally, we have these two behaviors, perpendicular or parallel, depending if the category of the point group. But we now can consider the case in which we have both mirror planes and rotational axis in the plane. And this means that in this situation, we will have a combination of the two extreme behaviors. So we have both cases, spins that are perpendicular to the wave vector and spins that are parallel to the wave vector. So essentially, we have here what we call Dresselhaus spin texture. So something very nice that I would like to mention here is the following. This tangential spin texture, called also Rashba, can appear in a topological insulator if the topological insulator, the surface of the topological insulator, satisfy these point groups. If we have a different point group, then it can be different. It's not necessary to be always helical. It can be any other possible pattern depending on the symmetry. And also, when we have this kind of a spin texture here that we call radial, is also known in papers as Weyl spin texture, we actually can see that there is a relation between the symmetry we have and the kind of a spin texture. And this is not related with topology. I mean, we don't need to have this Weyl semi-metal to have this kind of spin texture. But it turns out that most of the Weyl semi-metal like this are chiral. You know, most of these materials are chiral. So if you have a Weyl semi-metal, this kind of behavior, you will see that it's usually chiral, like tellurium, like I think tantalum, arsenide, and so on. So of course you will expect to have this kind of spin polarization, but not because the Weyl topology, but because of the symmetry of the point group. Okay, so now we can use these rules and translate them to compounds. I'm going to finish with this information. So look, now I can write here all the possible all the possible point groups I can find in materials. So we have 32 point groups, okay, in these 230 space groups, and I take all of them that are not centrosymmetric, and I put here in the headers of our plot. Okay, so we have here polar chiral, polar non-chiral, non-polar chiral, and non-polar non-chiral. Okay, and these are all the point groups for a material I can have that is not centrosymmetric. Okay, well, now in the y-axis here, I wrote all possible, again, point groups, but I can have in the reciprocal space. Okay, so we have now the intersection between these two plots. Let me put here a light. Okay, so we have the intersection between these two plots here. And well, you can notice here the following thing. When we have a gray color, okay, this means that the specific crystal point group cannot have this symmetry in the reciprocal space. Let me try to explain this, for instance. Let's pick up TD, that is the point group symmetry of the gallium arsenide, for instance. So this means essentially that we can have a K point in gallium arsenide that have the symmetry C1 or C2, look to the y-axis, but it cannot have any point group with the symmetry C3 or C4 or C6, and so on. So always we have a Y square. This means that the point group of the crystal can have this specific K point with this symmetry. Or in other words, there is a K point with this specific symmetry in the Brillouin zone of the material. And when we have gray color, this means that there is no any K point with this specific symmetry in the Brillouin zone of the component. Now, we also put here some letters W, D, and R that stands for the kind of spin polarization pattern we expect to each of these specific wave vector point group symmetry. For instance, as we discussed before, for C3V, we expect to have Rashba. So you will see that for all C3V here in the y-axis, we have Rashba, and always Rashba, okay? Always Rashba here. But when we have non-polar, non-chiral, we will have something like there's a house, and always there's a house. And now we can directly see some nice information. For instance, that non-polar, non-chiral compounds can have all possible spin texture we discussed before. Weyl, Rashba, Dresselhaus, in combination between them. Non-polar chiral compounds can have Rashba and Weyl, but it cannot have any Rashba, only pure Rashba spin polarization. As you can see, there is no any K point in non-polar chiral compounds that are polar non-chiral, okay? And this gives us a complete list. Now, if you have a specific compound, you can directly look to our table and then try to search which kind of spin texture you can expect in your component for the specific wave vector without do any calculation. So you can directly look at this, no DFT, no time binding, just look to the table and then have the answer, okay? And then we say, well, let's try to use this and for a specific example here. Okay. It's not. Okay, what happened? Yeah, okay, I don't know, but my screen is not changing. But you can see the slides.
It's changing here, Carlos. It's changing.
Okay, okay, thank you. Well, so now we can for instance use that for to filter components for specific applications. So the idea is the following. Now, if I take a component, let me try to change here. If I take a component, I can ask myself to the following question. What if I have one specific polarization, one specific K point, another in other K point? So if the energy between these two different values is very close to each other, then I will be able to control or access to these different spin polarizations and then use them in a device. So controlling the spin texture by accessing to different spin polarizations. So we try to do that. So we essentially took a very big database of 2,000, almost 21,000 components, and then we try to find components with this kind of behavior. I mean, multiple spin textures that are close to each other in energy. So what we did was first to remove components that are magnetic, pick up only those that are gap, select all components that have less than 20 atoms because we wanted to make the calculations for these components, and exclude also components that have F orbitals. Finally, we also, for instance, select components that are not centrosymmetric, those that are polar non-chiral, non-polar chiral, and non-polar non-chiral to guarantee that they have multiple spin textures. And finally, then we perform the calculations, and then we look to the dispersion of the band structure, and then we try to select those that have a linear spin splitting that is not have a linear dispersion here. So essentially what we did was select those with linear dispersion, but have this linear dispersion at different k values, okay? And with k values, we had different energy that is smaller than 100 milli-electron volts. So we did that, and at the end of the day, we got 37 insulators with multiple spin temperature shapes near the bend edges. So essentially, we have bend edges now that have multiple spin temperature, and you can select them and use them in different situations as you wish, depending on the component. So there are many nice examples. For instance, one that I really like is this germanium telluride. So in germanium telluride, we have the following thing. These two planes, Z and L, have different symmetries. For instance, this A point here have and the Z point have C3V, and the L point have the symmetry C3. Okay, so according to our theory, C3V impose a Rashba spin texture. So indeed, when we make a DFT calculation or time binding model for germanium telluride at the Z point, what we saw is a very beautiful Rashba spin texture here, okay? But at the L point, because of the different symmetry, which is C3, and have no any real, let's say, defined pattern, now we have a combination of patterns. So we have something that looks like Dresselhaus plus Rashba spin polarization. And this is what we found here, okay? So other example, for instance, is the silicon oxide. Is a very well-known compound with a very small spin splitting. However, again, when we look at this compound to the valence band maximum, what we saw is that at the A point, we have something like vial spin texture, and it's because this silicon oxide is a chiral compound, so we will see something like this vial spin texture. But when we go to the H point, which has a different symmetry, we will see a combination of let's say, canted spins and parallel spins. This is essentially what we call Dresselhaus spin texture. So we are able now to use our theory and search for compounds, and you will find a complete list of the materials in our PRB paper from 2 days ago. So just to conclude, we have that the spin texture can be predicted using the wave vector point group symmetry. So once you define the wave vector point group symmetry, you are able to a priori define the spin polarization. Also, we describe the relation between the real point group, of course, of the wave vector, to have the possibility of accessing different spin textures in the same component by changing the value you are looking at. I mean, let's say that, suppose that you can control it with an external electric field. We're trying now to do that. So I don't know if I have more time, but if this is the case, I would like to just...
Yeah, go ahead. Go ahead.
Okay, thank you. I would like to just leave here an interpretation of what I think that we should invest time on this field. Well, it turns out that we have the combination of magnetic and electric effects. So we, for instance, here in the y-axis, we have antiferroelectric, ferroelectric components or non-electric. And in the headers of the x-axis, we have non-magnetic, ferromagnetic, anti-ferromagnetic, or what is called alter-ferromagnetic. And it turns out that for each of these possible magnetic or electric effects, we have a specific kind of spin polarization in spin splitting. For instance, the anti-ferromagnetic spin splitting was recently discussed by Alex Unger, one of the co-authors of this paper that I just showed you. Discovered that anti-ferromagnetic ordering can induce spin polarization, okay, even when we have no spin splitting. But essentially, there is only one square here in which we have the interpolation between ferromagnetism and ferroelectricity, and this is essentially what we call, for instance, Rashba-Zeeman effect in multiferroid compounds. But there is no discussion about these gray squares, and this is what we are now investing time. And if you, I know that some of you know very well this kind of behavior, and I would like to discuss with you later about it. Well, just to finish, I would like to present an example of the control of the spin polarization by breaking symmetry. Now that we know that the symmetry actually impose the spin polarization behavior, we can see that if we have a compound, for instance, with edge states. Can you hear me? Hello?
Yes, we can hear you.
Yes,
Okay.
yes, we can hear you.
Okay, thank you. Well, if we have edge states, for instance, and this, well, the spin should be then perpendicular to the mirror plane. If we have a mirror plane in this kind of topological insulator, so this is essentially a TI, a two-dimensional TI, a quantum spin Hall effect. And then we have edge states here that are imposed to be in a specific direction because of the mirror plane. For instance, here, if we have mx plane, then the spin should be along the x-axis. However, what happens then if we break this mirror symmetry? Then the spin is not longer required to be perpendicular to the mirror plane because the mirror plane doesn't exist. So we can try to do that. And then we break the mirror plane using, for instance, an electric field. And by doing that, we are able then to change the spin polarization. So look, before we only have a spin texture in the x-axis, but now when we apply an electric field, we have a spin polarization in both x-axis and z-axis. So essentially, we are able to control the direction of the spin polarization using these rules of imposition of the direction of the spin polarization in terms of the symmetry. So, well, you can find more information of this paper here in this PR paper, and that's it. Thank you for your attention, and I will be happy to hear your question and discuss more about this nice subject.
Carlos, thank you very much for the very nice talk. So it's open to questions. I'm sure Edson has a question and probably Gerson too.
Hi, yes, I have one, but I was waiting to see if somebody else had another.
Go ahead, Gerson.
Okay, Carlos, thanks again for this is the second time I see this topic you're talking about, and both times were quite nice, so thank you. Last time I was asking you about the non-symmetric cases, and soon after your previous talk, I realized that I knew the answer as well. It just wasn't paying attention enough. So now I have another question that I think is related to something you were talking about, but I had to leave for a second. Maybe you said something and I missed it. So when you have gallium arsenide, but not bulk, the two-dimensional electron gas, you have basically the linear and the cubic Wesselhaus, and then you apply an electric field, you get the Rashba contribution, right? So without the electric field, if I remember correctly, you are in the D2H group, and then when you apply the perpendicular magnetic field, you go to D2D. But the point is, the texture changes, and when you apply the electric field, the spin texture depends on the intensity of the electric field because of the interplay between the Rashba and the linear or cubic Wesselhaus. Let's forget about the cubic between the linear and the Wesselhaus and the Rashba. You know, you can go from pure to persistent spin helix, adjusting the coefficients. So basically, it changes. So how does that fit in your model?
Yeah, this is a nice question, and thanks a lot for the question, and it's very nice to meet you guys again here. Thanks for the invitation. So, well, I forgot to mention that this work was done in collaboration with Gustavo Dalpian in the Federal University of BC and also Alex Unger. And I would like to thank also to FAPESI for the support. And well, in, in terms of that, in principle, the model should work when we go from one symmetry to another, okay? So if we change the symmetry, then we should able then also to predict what is happening in the component in terms of not only symmetry, but also the spin polarization. So we have here the case in which we have the interpolation between both Dresselhaus and Rashba. So we know that let me go back here. Okay, this plot. Yeah. So we know, for instance, that for, let's say, D to D, we will have well, according to what we had discussed, we will have a kind of Dresselhaus model, but for D to H, then, which is, yeah, D to H. Yeah, here there is actually a problem. For D to H, it should be, for D to D, sorry, it should be a combination of Rashba and Dresselhaus. But it's very nice to see the following. Look, when we have an electric dipole, right, an electric field, a perpendicular electric field, then we have a polar axis. There is a polar axis, right? So essentially, we are imposed to have a kind of Rashba behavior according to what we have discussed. However, we know that because of the mirror planes in the gallium arsenide, we also require the spin to be perpendicular to the mirror plane. So I'm not sure now when we look to the two-dimensional material if this is still valid. I mean, we can extrapolate all the discussion on 3D components to the materials. I think that in principle we can make a parallel discussion, okay, for two-dimensional point groups, but essentially here in our table we are only looking to two-dimensional point group symmetries. So I guess that we can write something similar for two-dimensional point groups in the case which we have an electric dipole. Or it's not really inside this initial discussion we have for the point group symmetry in the three-dimensional space. But I will try to solve that later and discuss it with you because it's a nice question. Definitely, it's a very nice subject. I mean, what happened in two-dimensional components?
Yeah, if I had to guess, based on your talk, I didn't do the calculation. Can you hear me? It feels like the internet is going on and off. I'm not sure if it's here or there. My camera is dropping sometimes. So if I had to guess without doing the calculation, is basically what the model will tell you is that there could be two types of textures, and then which one will dominate depends on parameters that go beyond group 2 itself, because arbitrary coefficients that will give you the final answer. I don't know, maybe something like that.
Yeah, definitely. I mean, when we have these low symmetry point groups, like let's say C2, C3, D2H, D2D, etc., we usually have a combination between more than one spin polarization pattern. So we have usually combination between Weyl, Rashba, Dresselhaus, Rashba, and so on. And then the details of the final polarization depends on the atomic species and how the parameters are determined by these elements. So, of course, we have non-symmetric symmetries, which are not considered here. We can indeed impose specific symmetry constraints to the parameters. So not only depending on the elements. And
okay.
another subject. Yeah.
Okay, just one quick question. So in the end here, you are showing that for perfect cases, there are three possible or combinations of these three possible spin vectors, which are the Weyl-Dresser-Haus and the Rashba. Okay, you're not talking about non-symmetric, but if you allow me to translate, if we go to the non-symmetric, is there any other could arise, or they also limited to these three types and these types?
Yeah. Well, I didn't do the calculation, but if I have to guess, I will say that for what I have read, that now we have symmetry constraints to the combination between these polarization. I mean, of course, we can have. I'm just here discussing cubic cases. Linear cases. I mean, when the Hamiltonian depends on k, but we can have cubic cases. I mean,
I'm talking about the linear case one.
Yeah, and then for the linear cases, non-symmetric symmetries, I guess that we will impose constraint to the parameters. For instance, if we have a combination between Rashba and Dresser-Haus, then we will impose in some cases a specific proportion between the parameters related with these two linear Hamiltonians, Rashba and Dresser-Haus. And actually, there is a nice paper about discussing that we call alpha and beta the parameters related with Rashba and Dresser-Haus respectively. Then in some specific non-symmetric symmetries, they are required to be equal. I mean, the same magnitude. However, I don't know if this can be extrapolated to all non-symmetric symmetries. And if we go to other kind of chiral or non-chiral symmetries, we will have a combination between, for instance, Weyl spin texture that also appears here, and Rashba, for instance, or Weyl and Dresser-Haus. So this is an open question, and it would be nice to invest some time on it. Yeah.
Okay, thank you.
No, thanks to you for your question.
Edson, you have a question?
Yep, I have a question. Thank you for nice talk, Carlos. And I have to say that I'm really familiar with all this zoo of class of symmetries, but I could grasp some ideas, and it looks like very interesting. And my question may be naive for you guys that are really fond of all these class of symmetries. But so in this sense, my questions may be very basic and too general. So since now you focus on chiral and symmetry, so to speak. So and I have been reading about these symmetry classification of several materials, and by Outland and Zerbauer, where they have time reversal, particle hole, and so they have a table, as far as I remember, it's 9 class of symmetries with these combinations. And so in your case, it's a different thing, or you can somehow, it's a sub class of those more general class described by these authors. I'm not sure if I was that clear.
Yeah, can you please repeat the three symmetries you mentioned?
So I think there was time reversal, chiral, and particle hole symmetry. So they were able to classify topological insulator and topological superconductors.
Okay, I got it.
So these are completely different zoo of symmetries, or somehow has some lie within some of those symmetries.
Okay, very, very good question. Thanks for your question. So it is the following. Look, we made a lot of restrictions to make our life easier. So for instance, we say, okay, let's focus on in 3D components. This is the first thing, the first constraint we put. Then we say, let's focus only on linear Hamiltonians. I mean, the spin splittings that are coming from linear spin-orbit coupling interactions. Then we also say, let's focus on point group symmetries that are not magnetic. So then, sorry, that are not magnetic. So let's remove our problem about time reversal symmetry, and let's suppose that all symmetries in the K points have time reversal symmetry. So we know that even in a component preserving the time reversal symmetry, we can have some K points that break that symmetry. However, we say no. Let's focus first. Now we are actually doing the magnetic version of this. I mean, what happens when we have a magnetic point group? This is a little bit more complex, but this is also very useful and nice. And also, we need to spend some time on the 2D version. I think that is also very important. So, well, then if we classify our systems in non-magnetic, chiral and non-chiral, we are only in a small portion of symmetries that are described in the let's say periodic table of topological insulators and superconductors. So we are not restricting our life to have a topology or not. We are comfortable if we have topological insulators or not. However, what we are saying is that if our system is a TI or not, and is in this small portion of the table, then we are able to say which kind of spin polarization we have, even if it's not TI. So it's nice, for instance, that we can have surface states that are not protected by any symmetry, but they have the spin texture of protected surface states. So only because of the symmetry. And this is, as I mentioned, only a small portion of the big, let's say, kita F table, okay? And what happened with the rest of symmetries? Well, this is a matter of time to invest and understand what are the relation of the other symmetries with the spin polarization. So we just need to how to say work more on that to understand. So it's a big world of symmetries, and we to invest time on it. Yeah, thank you for the question.
Okay, everybody. Thank you very much.
Thanks to you.
Carlos, I have a comment and a couple of questions, maybe not even sure completely about what I want to ask. Is something that is going on in my head. The comment is the following. I posted a DOI in the chat of a paper by your collaborator, Alex Zunger, from 2014, if I am not mistaken. Yeah, 2014, which discussed exactly this point that you mentioned about a layered system. I know about that because I was interested in this system. It was a superconductor, bismuth S2, sulfur 2, and lanthanum, oxygen, bismuth, and sulfur. And it's a layered compound, and it has two planes in the unit cell, and one of the planes you have broken inversion symmetry, and in the other two, but they are in a way that there is an inversion symmetry point between the two of them. So the rule would say that you shouldn't have spin orbit, right? Because you have a centrosymmetric system. If you have one point that if the system is centrosymmetric, then you shouldn't have Rashba, for example. But he found out that there was a huge Rashba effect in each one of the planes. So I think it's more or less what you were describing in your talk, in one of your that global symmetry doesn't tell the whole story, let's say.
Very nice.
I don't know if you know this paper. I put the link in the chat.
Yeah, thank you. I saw it, and this is a classical and very beautiful example of how local behavior can affect the global behavior, and of course phenomena that are determined by local behavior and not the global symmetry, the global behavior. For instance, we can say about the time reversal symmetry in an anti-ferromagnetic compound that we have magnetization up and down in two different sectors, and then we have a local behavior in each of these sectors, but the complete material have a total magnetization equal to zero. Yeah. So in this specific case, we have this analogous with the electric dipole. So one sector have an electric dipole, and the other layer have also an electric dipole. But it turns out that the electric dipole in each of these layers is such that it cancels each other. So we have an electric dipole here that cancels the other electric dipole. So eventually, we have I mean, we can expect a spin splitting, okay? So we have a spin splitting in each layer, but because of the total cancellation, it turns out that the spin splitting looks like degenerated bands, because the two bands, for instance, we can think that this is a spin splitting on one band, and this is a spin splitting of the other band, and this is up and down, and this is up and down. But if you put the two together, you will have up and down together, degenerated, right? But the degeneracy is between different layers. So this is up and down for different layers, for instance. We can think like this. So
can I understand a bit George's question? So have two layers and total have no inversion symmetry regarding respect to the center of the two layers, right? In the main distance between the layers. But if you look at a particular layer, it doesn't have inversion symmetry. So in principle, presumably you have some sort of structural inversion symmetry broken. So Hashband may appear, but they would be canceled out by the effect on the other layer, right? That's what you are saying.
Yeah.
Well, at least you will not see the Rashba in the band structure. You would have to look at the Rashba effect locally. He even proposed in another paper. He proposed, because this material is a layered material. Some people were comparing it to the cuprates in the beginning, because it's a superconductor that has a mildly high TC.
But you should be able to see. You should be able to see spin splitting if you have a surface result.
Yeah, exactly. That's the idea. He wanted to make a spin filter diode exposing one of the surfaces, because you can cleave it and have all the action in one of the surfaces only, and then you could think about a spin filter effect or something like that.
Yeah, and then the whole theory we describe here is, again, has an additional constraint. We consider only spin splittings that you can see in the band structure. This means only in materials that are not centrosymmetric. But it's equivalent. I mean, if you consider chiral, polarity, and these things for components that are centrosymmetric, you will also able to describe which kind of a spin texture. Even if you don't have any spin splitting, you will able to describe which kind of a spin polarization pattern we can observe in the band structure. So, and it's a nice thing, and it's in some way related what I mentioned before about the multiferroid components and these things. So it's everything about the whole local things is reflected in a global behavior. Okay, and how good are you in the lab to have a selectivity to choose the phenomena in only one sector of the compound? And I think that this is just an example of the dipole, but just let's think that we can do that with magnetization, or we can, for instance, do that with displacements of atoms in perovskites, or tilting in perovskites, or even for electricity. I mean, two layers that have a different current and these things. I think that is a very nice field. It's not like a new area, but of course, many people from different sides are working on these kind of behaviors. In different areas are approaching to the same kind of idea, the philosophical idea.
I would like, sorry, I'm interrupting George.
Yeah.
George,
no, go ahead. Go ahead.
To make a clean question because I'm interrupting all the time. But let me make a comment and see if I am right. You can correct me if I'm not. When everyone say the spin polarized in this type of material, since it has spin-orbit coupling somehow, it's not a true spin. It's kind of a pseudo spin in the sense that it's not the original free spin in the electrons, right? So this abuse of language, but it's fine. I just want to understand this is just some combination of momentum and spin, right?
You're totally right. I mean, this is
Okay.
not the real spin of the electron. This is true. This is a collective spin behavior. I mean, this is the expected value of the collective wave function. So we have a wave function for the whole compound. Can be mean sphere, can have a strong correlated phenomena, interactions, and these things. And what we have at the end of the day is the manifestation, okay, of the collective behavior of all the electrons in the compound, not only the specific spin of one electron. You are right. You are totally right.
Good. Second thing, when we talk about measuring of spin polarization, it should be like momentum selective, because if there is no time reversal symmetry broken, at the total spin current should be non-polarized. But if you are able to focus to collect a spin from a particular point or region of the Brillouin zone, then you should have polarized, but not if you don't select the momentum, right?
You are again totally right. I mean, if we don't have any time reversal symmetry breaking in the compound, or even as maybe TIs, that we have a very let's say energy difference between spins, so we need a kind of sensitivity in terms of the momentum.
Okay. Okay, thank you very much. So I'm happy that I got some.
Okay, that's good.
Sensible understanding. So George, sorry for.
Yeah, no, it's not exactly a question. Is a comment. I understand that the whole rage about topological insulators is that probably born out from the quantum Hall effect that became a standard for resistance measurement, because you can make your sample as dirty as you want, and you're always gonna have the resistance that is a quantum of resistance. So it became a measurement standard for resistance. So the property is very robust because it's topological. You don't need any symmetry. You don't need spatial symmetries. In reality, for the quantum Hall, is talking about the table that the Zenbauer-Outland table that Edson mentioned, is the one class of topological insulators that has no symmetry at all. It's the first one on the top. Has no time reversal, no charge conjugation, and no chiral symmetry. So the less symmetries you have, if you are topological, you have a property that's very robust, because you can start with a crystalline system that has translation symmetry. You can do whatever you want with it.
Yeah.
If it has that property, it will keep having that property no matter what, because it's protected by, in the case of quantum Hall effect, I don't know what it's protected by because there are no symmetries. But anyways, so one thing that strikes me as strange to understand is the biosystem. Because the biosystem is very clear that you have a point in the Brillouin zone where the spin polarization is either a source or a drain of spin polarization, right?
Right.
That's one of the discussions. But if it's a topological property, you don't need any translational symmetry. You don't need a Brillouin zone to have the property, because it's not dependent on a spatial symmetry. But if you don't have a Brillouin zone, how do you describe this source and drain in reciprocal space? Do you go to a continuous model where K is continuous, you don't have a lattice anymore? But then what distinguishes one point from the other if they are all equivalent? Why one point would be special? The only point that I can see that is special is the gamma point, the K equals 0 point. So I don't know if I am saying bullshit or if there is anything there, because it's strange to me that the property is described through a translational symmetry, the Brillouin zone, but it doesn't require the Brillouin zone to exist because it doesn't depend on the spatial symmetry. The Weyl system, in reality, is one that happens when you break inversion symmetry, for example. So you don't have even inversion symmetry. So that's something that I'm still trying to.
Nice. It's very nice because, something I think that this is in some way a paradigm is that we learn in our undergraduate course that we usually relate the phenomena with the existence of some specific crystal symmetry. So we always connect that. And this is what we have in our brain all the time. So the first question that appears, as you mentioned, is, well, if we don't have any symmetry, I mean, we have these quasi-crystal or some anything that we can define in terms of, let's say, disorder, for instance, then how to define the topological behavior? For instance, any topological behavior that we describe usually in terms of a Chern-Simons or a wave function, if you cannot now define band index and a K wave vector, so how to compute that? And then it turns out that, in my opinion, it's not a problem of the phenomena, of course. It's a problem of our interpretation of how see the whole world of crystals, right? So we always are thinking on symmetries, but then our description, mathematical description, is based on the symmetries. So to try to answer the question or continue with the discussion about Weyl, which I think that is very beautiful, let me try to ask you the following. What is protected in a Weyl semi-metal?
Well, I'm not.
I think okay. George is unprotected. George is unprotected. He was sunk.
Of time reversal and inversion symmetry, you get a Weyl semi-metal, and then the nodes will slide to different places in the Brillouin zone. So that is my
yeah, I think so. I think you're right, George.
Yeah, this is. But, I totally agree with you, and this is. I think that is like the flux of the Berry phase. We can say something like this. I mean, when we make the integration of these you mean, kind of monopolar magnetic things in the nodes, sorry, in the Weyl, then we can think that this is the flux. So then comes the go ahead, sorry. I think that I mean, the flux of the very phase, you can even define if we don't have a periodic system. This is one thing. However, I'm not sure if the picture we have in wire semimeters, that is always coming, spins coming, is required always. I mean, we can have many different ways to cancel this flux of the very phase with other kind of spins. I think that these spins are only appearing because of the specific crystal symmetry we always see. But if you have a disordered symmetry, it will still be valid. However, it will have a different kind of spin texture. This is what I think. I don't have proofs of this, but this is just as you say, trying to think and discuss about it.
I think I have my interpretation is that if you go back to the original paper by Bernevig, where he predicted this value, I think Bernevig, right? So apparently there you actually value is long time ago, but Bernevig put his fingers everywhere, so we always bump into his paper somewhere. And apparently group symmetry is in the more general model is responsible for the existence of those bands. Then when you go down to low energy models, you lose those information. So when you work in the continuum model that valid in some particular point of the Brillouin zone, say the gamma point, for instance. So then you have 4 bands, but what are the symmetries that protect those bands are left behind when you somehow fold down your larger Hamiltonian into these low energy Hamiltonians. So then but if they are still degenerate, you have 4 bands, they are degenerate. So the Dirac point cross at the same point of Brillouin zone. When you calculate the topological invariant, you get 0 because they have opposite signs. But then when you break time reversal symmetry, for instance, so you shift this band to a different point of Brillouin zone. So when you now calculate some topological number, it doesn't go to 0 anymore because they are in different positions. But I think the symmetry that protects this band are left behind in the more general field.
Yeah, I remember that. Yeah, that's yeah, definitely. So the point is that, you know, something curious is that we can have what we call vial spin texture in a component that is not vial, right? And then the question is really this kind of spin texture required to be vial or not?
Yeah, that was my next question was that.
So now your next answer apparently.
Yeah. No, I was going to ask that. Did you look for any protection when you saw that vial texture? Did you say, well, okay?
And it's kind of curious, but we can have a material that is not vial at all with this kind of spin texture. For instance,
but
oxide.
As long as you have the crystal symmetry protected, then you have vial. You have a vial-like point, let's say.
Exactly.
Okay.
That's correct. So,
yeah.
And then
that I can understand. That is easy to understand. You explain very nicely, showing if I have a plane, it has to be like that. If I have an X, it has to be like that. If I have a certain combination of symmetries, then it has to come all to the same point, and that all makes sense, and it's protected by that. But in the case of vial, I struggle to understand. of the true value, let's say, the true value.
Yeah,
There,
exactly,
it seems that there is something very profound behind it that, as you said, we have these crutches that we use, that is the Brillouin zone. We describe everything using the Brillouin zone, even when it doesn't exist. So
yeah, exactly.
So that's the case when you work on low energy model.
yeah, I guess so. I guess it's something similar, because then you have your reciprocal space doesn't have any symmetry, or better, it has all the symmetry. It's spherical. So the point is that then no point is better than any other point aside from the center of the reciprocal space.
Unless you move the cylinder far away from the from zero.
Yeah, but I don't see anything special to the point where the node goes. This point or that point, they are all the same. From the symmetry point of view, they are all the same. They don't. So which one it should? I would say that it should be like that.
They have opposite charge, topological charge.
Yeah, no, I understand. But what I am saying is that there is no point that is better than any other point. Any direction that's better than any other direction. Okay. So which one should it go? That's the, so as you said, probably the model misses an important information. That is, it's just borrowing from the old model to decide where to go, or something like that, I don't. Well, but we are almost 2 hours here. It's very when we have long discussions, it's because the seminar was quite good, and